So I'd like to welcome everyone to this webinar, Unlocking the Power of Europe PMC's Machine Learning Dataset, Discovering Drug Targets with OTAR and Open Targets. I'd like to introduce our first speaker, Santosh. He's the Senior Machine Learning Developer at Europe PMC with a PhD in computer science and a keen interest in machine learning. So Santosh, if you could start.
Thank you very much, Samar, for introducing me. So let's dive into the webinar. So next slide, please. So I've divided this webinar into 7 chapters. In the first chapter, I will introduce you to the Europe PMC. And then in the second chapter, I will talk about the annotations in Europe PMC. And then these annotations have been tagged using dictionaries. And in chapter 3, we will discuss about the problems. And in chapter 4, why there is a need for curated annotations. And in chapter 5, we will see how the Europe PMC annotations dataset has been developed. In 6, we will see the results, and in 7, we will discuss the impact. So next. So Europe PMC partners with PMC in the USA, produced by the National Library of Medicine via the PMC International Collaboration. We are a repository of choice for several international science funders. We have around 50 million records at the moment, and it's growing day by day, including articles, preprints, documents, protocols, and books. Chapter 2, annotations in Europe PMC. We have around 1.9 billion annotations, ranging from gene proteins, clinical drugs, metagenomics, diseases, to accession numbers, cell lines, anatomy. And all this is possible through Europe PMC's platform. We have a annotation submission system where we submit annotations to from in-house Europe PMC text mining annotations platform, as well as from third-party annotation providers as well, which includes open targets. And these annotations are stored as JSONs, which can be extracted through using annotations API, and as well as visualized on the web on the Europe PMC's web interface using Scilite annotations tool. We not only provide annotations, but we also provide grounding to the knowledge bases. For example, here, angiotensin converting enzyme is highlighted using the Scilite annotations tool, but also it is linked to the UniProt ID. Chapter 3. So we have done these annotations through dictionary tagging, and we face some kinds of problems. Dictionary for text mining is like going on a tour with a map on. So for example, if we have precise and accurate map, then we go to the right destination. But if we not, then we might reach a wrong destination, or we might not reach a destination at all. So dictionaries are a list of patterns. For example, in this case, this is biomedical entities. So these are extracted from several different resources. So for example, for diseases, we use UMLS here in Europe PMC, EFO and NCBI taxonomy, and we use SwissProt for gene protein annotations. So we take the mentions of text from these resources, and then we pattern match using regular expressions and identify the entities in the articles. So this is how we do dictionary-based pattern matching for identifying entities. What we like about dictionaries is it's easy to understand, interpretable, explainable, and easy to implement. What we don't like is the lack of use of contextual information. Dictionaries are static, and they don't use the context information. And it requires a long list of exhaustive recalls, and that's where we will have to keep. That's where the list keeps on increasing to recall more and more entities. So we will see these problems now. So, for example, to represent NFKB, it's not just representing NFKB, but we have to come up with an exhaustive list of nuclear factor kappa B, nuclear factor KB, etc. Next slide, Summer, please. And then the linguistic nature of biomedical text also leads to accuracy challenges. For example, in dictionaries, we represent just P53, but this P53 could be a gene P53 in one instance and protein P53 in another instance. So all this leads to accuracy challenges. And acronym ambiguity. So GPI in one instance, it could be a chemical. In another instance, it could be a gene protein. And for example, next slide, please, Sama. In one case, RP could be retinal pigment epithelium, a disease, or in another case, it could be a variant of a gene protein ribulose 5-phosphate epimerase gene. In another instance, it could be ribulose phosphate 3 epimerase gene. So there are several variations of this of RPE, the word RPE, and this leads to ambiguity. So in overall, we will see a lot of false positives and also false negatives. The false positives arise for several reasons, which we have witnessed now on the acronym ambiguity, RPE, and GPI, and then the contextual differences to identify terms. So AIDS is the right term, but in one instance, AIDS is a disease, but in another instance, it is to support hearing aids in another instance. And common English words. CAN is a right, it's a gene, but then it would be a verb as well. It is a common English word. And then with dictionaries, we also fail to understand the compound entities. For example, BRCA1 and 2, we could only detect the BRCA1 with dictionaries, but we would miss on and 2. So we would miss BRCA1 and BRCA2, or BRCA1/BRCA2. And then in false negatives, there are many missing entities that are not existing in original dictionaries. For example, T2DM for type 2 diabetes mellitus. So we would miss T2D, which is another variation of representing type 2 diabetes mellitus. So we would miss on new entities and other entities which are right in there, but we would miss on tagging them. So why would we need the curated annotations? We will see in chapter 4. So we have seen two types of entity-based methods. One is dictionary and another is the rule-based methods. And now with the popularity of machine learning, we are diving into the machine learning era. So what we like about machine learning is we don't need dictionaries. And machine learning are really good at using contextual information. So we will have less ambiguity. But what we don't like about it is difficult to interpret. It's a black box, especially with the new deep learning based approaches. And it requires manually curated data sets. And that's where we will lead to our chapter 5, that is development of Europe PMC annotated dataset. So as of 31st August 2018, when we started this project, Europe PMC had around 6 million full text articles in them. But then we wanted to select few articles, a subset of articles as gold standard, which we wanted to give them for annotators to curate. So we have taken open access and CC BY license because it's open access and it's CC BY, and we have around 1 million full text articles which we were licensed to use. And we also wanted to further go through the subset and select fewer articles from them. And that's where we selected few articles. That's where we came up with article size based selection. So for example, we thought the article sizes which had more than 50 KB would represent review articles, which would have several disease gene and organism based mentions, and the articles which had body size lesser than, let's say, 25 KB would be a case report or other reports which would not have any mentions at all. And when we did the further selection based on the article size, we were left with around 500,000 of articles. Again, we had to come up with several strategies here to select the final subset. So that's where we came up with the binning approach. So we did some kind of entity-based distribution and then selected articles in such a way that we have representations of low, low, low until high, high, high. So the low bin would represent low mentions of disease, low mentions of gene protein, and low mentions of organisms. And a high bin would represent high mentions of disease, high mentions of gene protein, and high mentions of organisms. So we had around 27 bins representing all the variations of low, high, and medium mentions of the entities. So on an average, the disease mentions were almost the half of the size of gene protein mentions. And this really helped us to set the boundaries for the final articles based on a stratification approach. So we selected 300 articles out of 500,000 articles based on entity distribution in a stratified approach. So next slide, please, Summer. So if you see this distribution carefully, we see a pattern here, and we discarded the low mentions, the low mentions of the entities here, because we didn't want to have articles with low mentions, and also they are a very high representative number here. So we discarded the low mentions of the bin here, and then we selected the 300 set in a stratified approach, such that the representations are represented in a stratified approach. So we will have the exact same distributions, but then we will have selected fewer articles from each bin in such a way that they have a very good representation. So now we have 300 full text articles, which we call it as a gold standard article set for us. So we gave these article sets set to annotators for the annotations, and for this we have used the hypothesis tool. Next slide, Summer, please. So this hypothesis tool is a open source tool for annotations, and it is available through Chrome plugin. And we have integrated this hypothesis plugin into our Europe PMC's platform. And we have explained the curators from Molecular Connections, which is in India, on how to annotate using a prescribed annotations guidelines. So the annotators have used this tool on the Europe PMC's platform to annotate the entities mentioned. So, for example, the annotators were asked to use the prefixes such as CRT, that is correct, MIS, that for missed, WS for wrong span, and WT for wrong type. So, for example, if we see this scenario here, defect is wrongly tagged, so WT_DS by dictionaries as a disease. So the annotators, they marked this, and they have curated this as wrongly tagged DS. And for example, if it is a wrongly tagged gene protein, they have annotated this as wrongly tagged gene protein. If there is a correct mention, then they would mention this as correctly tagged gene protein. So for example, stat here down, it is correctly tagged gene protein. If there is any of the entities missing, they would mark the new, they would create the new entity, and they would tag it as missed_organism. For example, in this case, this organism was missing from our dictionary-based annotation. So this is tagged as miss_OG. And for example, if there is a wrongly tagged organism, and then for the rightly tagged disease, so WT_OG is wrongly tagged for wheat here, because it is representing wheat stripe rust. So this whole span was detected as a disease. So this is wrongly tagged OG, but then the rightly tag is the right tag is disease. So this is represented as WT_OG, DS. So this way, the annotators have marked for all the possible annotations using the hypothesis tool on the Europe PMC's interface. So we have done around 4 batches of iterations with the annotators, and then in the first 3 batches, we updated the guidelines necessarily, and all this was done anonymously. So it was a triple anonymous based annotations. So the annotators didn't know who was annotating and what were the annotations. And based on the iterations, we have updated and corrected the annotations. So this is how we have generated the corpus. And now let's see the results in chapter 6. This is the distribution of the correctly tagged gene proteins and wrongly tagged gene proteins with correct tags for other entities as well. Similarly, sorry, Samar, please, yeah, thank you. And the entity tag distribution of the corpus and the comparison here shows that the annotators were mostly in agreement. So this shows that there is a high inter-annotator agreement. And for our gold standard annotations, we have taken the maximum vote approach. So for example, if 2 annotators annotated it as a right annotation, then or a wrong annotation, then we take the maximum vote and tag it as a wrong or right annotation. And when we have compared each and every annotator's annotations to the gold standard annotations based on maximum vote, we have achieved 99% accuracy. This shows that the Europe PMC corpus, the annotations corpus, is really of high standard with the high annotator agreement. And here from this image, we also can see that there were many missing gene proteins, which are false positive, false negatives actually, and they were rightly added back to the system. And there were many correct gene proteins as well. And then there were many missing entities which were added back, and there were many wrong entities which were false positives, which were corrected, and the falsely tagged dictionary annotations have been removed as well using this approach. And the bonus here is we not only ask them for the curators to annotate the entities, but also ask them for associations as well. So for this approach, we have considered the annotations, association annotations from the open targets submissions to us. So the curators have gone through the annotations of gene disease associations, and if there was a right association between a gene and a disease, then they mark it as yes, gene disease association. If they found that the association was not correct, then they mark it as not a gene disease association. And if it was ambiguous, then they tag it as ambiguous. And here as well, we see that there is a high inter-annotator agreement as well. So this annotations association dataset is also now made available publicly with the entities dataset as well. And all the annotations marked for entities are available in IOB format as well, which can be really given to any machine learning algorithm and can generate models for inference. This corpus, Europe PMC's annotations corpus, is the largest human-annotated biomedical corpora, which is publicly available now. And we have made all the annotation guidelines, code, and dataset publicly available on our GitLab repository. And we also have released our preprint recently on bioRxiv. Impact. We believe that this corpus will accelerate the life sciences research because it can generate several deep learning models for various applications, including entity recognition, gene disease associations, and sentiment analysis. And we also believe that this will support advancements in scientific research. The best example is Open Targets, which is using our dataset now. for drug discovery and disease diagnosis. And the models which have been trained on this dataset, the deep learning models using our corpus, are now being used for literature mining for open targets. And we will see in the next session about this in detail. So if you have any questions, please shoot. And then if you have any other further questions, you can always send it to our help desk. Thank you. And I'm really sorry for all the mess up on my system. I don't know, suddenly it gave me a hand. Thank you very much.
Wonderful.
Wonderful.
Wonderful. Thank you very much, Santosh. That was very impactful and interesting.
Interesting to hear.
Sorry, Santosh.
Sorry, Santosh.
Thank you. Yes, I hope everyone was able to bear with us, and thank you for your patience between the technical difficulties and me doing the slides. If all questions could please go in the Q&A, and we will get to those at the end of the session. And right now, I would love to hand over to our next speakers, which are Helena, which is the communications lead of Open Targets, and Annalisa, the Open Targets project manager, to explore entities for target disease prioritization. So please do share screen.
Thanks, Emma, for the introduction. So so hi everybody. It's nice to see so many people here today. A little bit nerve-wracking because we haven't presented this before, so bear with us. But yeah, so I'm Helena. I'm the communications lead for Open Targets, and Annalisa, who's with me here, is the product manager. So in this section of the presentation, as Santosh introduced, we'll showcase how we made use of this data set in the Open Targets platform in services of our overarching goal, which is to systematically identify and prioritize targets. So I just wanted to start by actually introducing Open Targets, just in case you were not aware of who we are and the kind of things that we do. So Open Targets is a consortium. It's a pre-competitive industry academia partnership, and you can find out more at the link that's at the bottom, opentargets.org, but I think you'll have access to these slides, so you can also check that out later. So the consortium is currently made up of 7 partners, which you can see here on the slide. So we have 2 academic partners, and we currently have 5 industry partners. And the idea is that all of these partners collaborate on a portfolio of experimental and informatics projects. And what we really hope we're doing is that we're bridging the gap between academic research and pharmaceutical drug development. Our overall aim is to help researchers select the best targets for the development of new therapies. And so to that end, we have 2 broad aims, which are represented by our 2 research programs. So on we have an experimental research program, which focuses on the generation of new experimental data that either supports causal associations between targets and diseases or provides a foundational understanding of disease biology. So the reason for this is that we figure the more you know about a target disease pair to begin with, or the more you know about the disease that you're trying to develop a new drug for, the more likely your drug is likely to be successful in clinic. And so our experimental program has 3 focus areas. These are oncology, immunology and inflammation, and neurodegeneration. Alongside this, we have our informatics program, and this focuses on integrating existing public data that provides evidence to associate targets with diseases. And this again is to help with target selection. So if we know that there's so much data out there, if we can bring it all together in a way that's systematic, that's harmonized, we can help researchers see what already exists, what we already know about targets and diseases, and hopefully that can help them select the best target for drug development. And so one of the projects that's in our informatics portfolio is the Open Targets platform, and it represents this aim really, really well. So the Open Targets platform, which is available at this URL here, platform.opentargets.org, it's an open source project, so you can go check out our code if you're interested. And we have a variety of different access options. So today we're going to focus on what it looks like in the web interface, just because it's a really good way to demo it. But you can also check out our data through a GraphQL API. We make our data available through Google BigQuery, including as a public data set. And we also have data downloads, so you can just download all of the data sets and take a look at them yourself. The main takeaway that I want you to take from the slide is that it's really a big data platform. So we have over 20 different data sources. We bring together a wide range of data types, and all of this like, as I mentioned, and I'm going to say this a few times, but to try help people select the best targets. And so the aim of the platform is to systematically identify and prioritize drug targets. The way that we do this is by integrating evidence for the association of targets and diseases. We harmonize that to a schema and we present it to the user in a way that we hope is kind of intuitive and comprehensive. So the platform is built to help make these connections, these associations between targets and diseases. And you can see that represented on the schema that I have on the slide here with that little connection between targets and diseases, that evidence that we integrate. And we have three entities in the platform. These are targets, diseases, and drugs. So we showcase information about all three of these entities and we build up the connections between them. So to give you an example of what we mean by evidence, so drugs themselves are a source of evidence because you can connect them to targets through their mechanism of action, and you can connect them to drugs through their indication. So this gives you an idea of the kind of evidence that we have that will connect targets to diseases. So we ingest a lot of data in order to build up the evidence for these associations, or we also have a lot of information that what we call annotation information to provide context to all of these entities. So for example, we'll try and provide you with as much information as we can about targets. And for example, what we know about targets, what we know about how safe they are, how tractable they are, that kind of thing. And so now that you know all about the Open Targets platform, how does text mining fit into all of this? How does the literature pipeline fit into all of this data? I think we can agree. So bibliography is a really unique source of information to try and identify targets and try and identify associations within the whole of the literature, because basically the literature represents the accumulated scientific knowledge that's driving therapeutic innovation. So it's a really good source of information for us. And so what we want to do with this is we want to be able to systematically query that knowledge to provide researchers with the most relevant information. To be able to tell them, like, here's what we have out there, here's what we know is in the literature. And just almost 2 years ago now, we had a massive rewrite of the Open Targets platform. So we called it the next generation Open Targets platform because so much work went into this. It was 2 years of work. It was a completely new design. It was kind of reimagined to help facilitate the building of therapeutic hypotheses. It had new features. We completely refactored the code base. And so part of this rewrite was an entirely new literature mining strategy that was based on the work that Santosh has just presented to you. And it really considerably improved the quality of the information that we were presenting within the platform. So it's super exciting that we're able to talk to you about it today. It also considerably sped up the process. So the entire pipeline now only takes an hour and a half, which is a massive, massive improvement on what we had before. So we use that data set in two different ways. So the first is to extract evidence for the associations of targets and diseases. And the way that we do that is through co-occurrences. So if the target entity and the disease entity occur in the same sentence, we consider that a piece of evidence that they are associated. To be more specific, actually, it's the aggregation of all co-occurrences of the same target disease pair within one publication that we consider to be one piece of evidence. But this evidence that we get from the literature will come and complement the other evidence that we integrate for different associations. So, for example, it'll sit alongside our genetic evidence or our animal models evidence, for example. The second way that we use the dataset is to provide context to our entities. So if you're browsing through the platform, for example, and say you want to know you're researching cystic fibrosis, we'll have a widget that will show you all of the papers that we have that are linked to cystic fibrosis so that you can look at those. The problem is that there's something, I think I checked this morning, it's something like 35,000 different pieces of literature that are associated with cystic fibrosis, which is a lot for one person to get through. So one of the things that we did with this is we developed an additional machine learning pipeline that sits on top of this and that tries to suggest similar entities in the literature to the one that you are currently looking at. And the idea here is to kind of suggest connections that may be interesting, maybe similar entities that you may not have thought of, and also to help you narrow down the list of publications that you're looking at. And I just like to define what we mean by similarity here. So an entity is similar to another when they are both likely to co-occur surrounded by the same entities in specific sections of publications across all of the literature. So what we're trying to find is other entities that are mentioned often in the same sections of the publication, hopefully showing you something that's maybe very interesting, very relevant for your research. So what does this actually look like? So I'm just going to describe a little bit the pipeline that we have. So the first thing that we would do is we use a dictionary-based approach to ground the tagged text from Europe PMC's dataset to the platform entities. So we have 3 entities, as I mentioned: targets, diseases, and drugs. And we get these from different sources. So our source of targets is Ensemble, our source of diseases is the experimental factor ontology, and our source of drugs is Kemble. And we use the nomenclatures from these sources as our canonical IDs in the platform. So one of the first steps that we need to do is to take the entities that we get from Europe PMC's dataset and tag them to the entities that we have. So we do this by applying a set of standard NLP tools. And this is disambiguated so that no matter how an entity appears within the publication, we recognize it as the same entity across the whole of the literature. So this is what feeds into our association evidence. So our evidence for the associations between targets and diseases. So let's say, for example, if you have a target, say CFTR, and you have a disease, so for example, cystic fibrosis, if I carry on with the example I had earlier. So if these 2 entities co-occur within a sentence, that's evidence for the association of CFTR and cystic fibrosis. So that's the first part of this pipeline. We then have a second part, which is a machine learning model, as I mentioned. And in this case, we use the matched entities to train a word-to-vec skipgram. The result of this model is a set of vectors. So each vector represents a normalized word embedding from our target, disease, and drug collections. This allows the user to find similar entities to the one that you've selected. So similar entities based on the vector. And as you select additional entities, it will narrow down the list of publications to the ones that mention all of the entities you have selected. And Annalisa will do a demo of what this looks like in a second, so you can see what this looks like when it's implemented in the platform. And so this work is what's used to populate the suggestions that are in our bibliography widget. So this widget displays all of the available publications for an entity, and then it'll in the little chips that you see here, it'll suggest similar entities in the literature to help you narrow down the list of publications. And as I mentioned earlier, this entire pipeline takes only an hour and a half, which is massive, massive improvement on what we had before. That's everything I wanted to tell you about the pipeline just now. So I'm going to pass over to Annalisa if you'd like to take over the screen sharing so she can show you what this looks like in the platform.
I will, yes. So hi, everyone. So my job today is to give a little demo and make you visualize all the impact and all the nice things that we can do with the Europe PMC data. So this is an awesome pipeline. Santosh has gone through all the text mining, and Elena has introduced to us the word-to-vec, but now it's important for you to see what it means for our products. So let's start with the first example. So as Elena said, the first way we use the Europe PMC data is to integrate the text mining data for us to build up new associations of evidence between target and disease, because the Open Target platform as a main aim to associate target to disease and then these 2 entities with drugs. So this is everything we care about around this platform. So let's start with Node2, which is a target, a gene, and it's a very nice example for us to show you the text mining results. So I'm going to start with this page, which is the Open Targets Association page. This is the core of our data. So as you can see, we have 497 diseases or phenotypes. Those are all EFOs mapped, as Elena said, associated with Node2. And all this data, evidence that we gain, evidence of this association that we gain from different sources like genetic associations, somatic mutation, drugs, pathways, text mining, RNA, and animal models. They are all condensed into this very nice array of data. And as you can see, for example, going back to text mining, there is an association between NOD2 and Crohn's disease that is supported by genetic associations, genetic data, for example, but also by text mining. So this is where the data from Europe PMC and from the pipeline Santosh described is actually helping us to get information about a certain disease and linked to a certain target. So if I now click on the Crohn's disease NOD2 line, you see that there is an evidence page, again, with all the data that we gain from different data sources, supporting the link. And you can see that there is like a nice dashboard with different data sources, and Europe PMC is one of them. So if I click on the Europe PMC dashboard, you can see that we have a big number of entries, so big number of papers or patents or preprints, because we are now integrating matches from these three publication types. They actually support and have evidence that NOD2 and Crohn's disease are actually mentioned together in any part of the publication. And this for us is very good evidence, because publications are like the best knowledge we can have at the moment. This is like very strong evidence that there is a link between this gene and this disease. So for example, if we just want to check this publication, 2015 publication, and we want to click on show 3 match details, this is exactly what Santosh was showing at the beginning. So there has been a match through the text mining pipeline between Crohn and NOD in 3 places of this publication, 2 in the abstract, 1 in the title. And this is a nice example because it's just 3 matches, but you can have publications where, or reports where the matches are quite a lot, and you have a list of them and a list of the places in the publication where these are mentioned together. So for us, this is again very, very good evidence that there is a link between Crohn's and NOD that adds up and complements to the data that we get from animal models or from open target genetics or ClinVar. And this is to show you the matching and the text mining data. But as Elena said, we use this data in 2 ways, right? So we have another pipeline, which is the Word2Vec model that allows us to use the Europe PMC data even beyond text mining. So we use this data to actually find new links between entities, so links between targets, drug, and diseases that are not picked up from the match because they go beyond the association. So for example, I have an example with cutaneous melanoma. This is a disease that, as you can see, has been associated with more than 3,000 targets in our platform. So we have quite a big chunk of knowledge on how cutaneous melanoma interacts with different genes and is associated with different mechanisms. And as you can see again, if you check, those are the list of targets that are associated with this disease. As you can see, we have text mining evidence from many of them, of the associations, for some of them quite strongly scored, because our associations here are scored by open target association evidence. We have some drug data from Campbell, for example, that is associated with this target disease pair. So we have lots of information there. But just to go beyond what we have from the data integration pipelines, if we click to on the profile page for cutaneous melanoma, where we have all the annotations and information we have on the disease itself. We have a bibliography widget, which is built on the Word2Vec pipeline model Elena was describing. And if I go down and scroll on the bibliography widget, this is a very, very nice tool that we recently, as Elena said, provided to the users to explore the universe of publications, so knowledge that, like deep knowledge, to explore the universe of our entities. So for example, here for cutaneous melanoma, of course, you have a list of publications and reports that link cutaneous melanoma to, that they talk about cutaneous melanoma. So here we are really exploring like a vector of information that in n dimensions and directions is actually pointing melanoma into the corpus of the entire corpus of literature. So we have loads of course, information on cutaneous melanoma. But what's really cool about this bibliography widget is that because of this similarity model, we can actually have, so the system and the platform actually gives you some hints of vectors or knowledge that interact with cutaneous melanoma. So we know, and all these entities that are linked by the model to cutaneous melanoma in this initial state are actually here listed by score. So for example, this plastic nevus is actually the vector that is closer to cutaneous melanoma. So this is telling us that according to the corpus of literature, there is a very nice interaction between cutaneous melanoma and this plastic nevus that we should, or a user should want to explore. But also if you wanna just go on with the exercise, let's say myself, I just wanna narrow down this universe and I just wanna check if there is a nice interaction between cutaneous melanoma and drugs. So I'm actually exploring, recomputing and exploring on the fly other interactions between entities. And we have now some drugs that the model is suggesting as linked to, in a way, on the corpus of literature to cutaneous melanoma, because they are mentioned in the same way around the same entities, in a similar way around the same entities in the corpus of literature. And for example, I know that vemurafenib is a drug that is used to cure cutaneous melanoma. So this is actually a very good positive test that the model is suggesting a drug that is very relevant to cutaneous melanoma. But just because I know, of course, here a user wants to explore unknown links. And also, let's say now I want to have some clue whether there is a target that links cutaneous melanoma to the drug. So if there is a target that the drug, I want to know which is the target that the drug targets. So if I click on the chip target, I can actually see that BRAF is coming out. And BRAF is actually as known as a target for vemurafenib to cure cutaneous melanoma. And this came up just when I narrowed down the universe of entities. So cutaneous melanoma interacting or intersecting with vemurafenib. And then there was a recompute. I just want to know the target, and BRAF came up into the picture. So this was just a positive example exercise to give you that there is endless potential in this bibliography widget. And so this is a very nice collaboration between Europe PMC and Open Targets, because there are, we go beyond text mining, we go beyond an association, we can actually explore 3D and dimensionally the links between entities. And I think I actually ran a little bit over my time. So Elena, I pass it to you, and then we might have questions later. do you want to share again?
Yeah, I won't. So I won't share my screen just in the so we can get to the Q&A. I just want to say thank you so much for listening. If you can take a look at the slides, I've included a few additional links that you might want to take a look at for further reading, which I will also pop in the chat just now while we do the Q&A, so that we can get straight to the Q&A. So I'll pass back to Summer.
Wonderful, thank you both very much. Yeah, so I've also popped the Open Targets link straight into the chat as well for you guys. So I'm going to start with one of the questions we have is, I think that's aimed at Santosh. How do you deal with common type authors writing?
Yes, with the dictionaries, there is a problem, the common typos and the other issues, because we cannot maintain an exhaustive list of all the variations of how the scientific authors write the article. And that's where we were moving to a machine learning based approach, because based on the context, the machine learning can detect these typos. And also, as Helena mentioned, the word vector approach, and there are several other techniques now based on the similarities. Even if there are typos, the machine learning can easily detect those entities for the correct annotations, for the correct tags. So machine learning way works better, and not the dictionary-based approach for identifying the typos.
Wonderful, thank you. And then for open targets, how can we find the right variant with sequence and open targets genetics? Don't know.
Yeah, given that this is kind of focusing on the text mining and open targets platform. So I think we can put some elements of this in the chat if you like. But yeah, I think we should move to a different question, and I'll try and answer that separately. Yeah,
that's okay. So how is the target disease association score, the overscore, measured?
I can take this one unless you want to take it, Annalisa.
It's okay. I'm actually replying to some.
Okay, cool. So
you can actually reply to this one. You can reply live. Yeah.
Okay, sure. So how is the overall score calculated? So the overall score is a combination of each of the scores that we give to the data sources. So each of our data sources will get a score. This is based on the kind of information that's there and the amount of evidence that's in the data source. These are then combined using a harmonic sum, which is what creates our overall association score. So the data sources are weighted. So for example, we might, a data source that we have a lot of, that we trust, if you will, where we know that the information is reliable, for example, because it's been curated, will have a very high weight, whereas one which is maybe predicted will have a lower weight. That is, in a nutshell, how the association score is calculated. That's the word.
Thank you. And kind of there was a second part there to follow on from that. So what sets apart the direct and indirect evidence scores?
Yeah, so thanks for reminding me. Yeah, so the direct score will only take into account any evidence that is directly linking that target to that disease. So within the platform, we have within our ontology, we have what's it called? Like a family of diseases. So if your disease might have several child terms, so for example, Crohn's disease might have a few child terms, those are indirectly linked to your target. So in our evidence page, we will show both direct evidence, which is, for example, any evidence that links node 2 to Crohn's disease. We will also show indirect evidence, which is any evidence that links node 2 to a child term of Crohn's disease. That's how we differentiate direct and indirect evidence.
Wonderful, thank you, Helena. And this one, I believe, is for Santosh. Will the immediate data sets of the pipeline also be available for this part?
Yes, they can be made available, yeah, because everything from Europe PMC is archived, right? So we know exactly when the date when we froze the open access dataset, and then how we have selected the articles. So yes, yeah, they can all be available, yeah.
We've had another question come in saying, how are you addressing the so-called reproducibility crisis problem? I think that might be more aimed at Santosh. I don't know if Helena also has something to add.
I
Yeah, I think the question is directed to me. Yeah, so everything what we have done is documented, and we have the sources to reproduce them, because we did use version control, and we have the frozen access set of at various intervals. So yeah, so this can be reproduced, and we usually work according to the pair principles. So so I assume that this will answer the reproducibility crisis problem, I guess. Yeah.
Thank you. We've got another question saying, is it possible that entity co-occurrence mentioned in one publication is also referenced or cited within multiple other articles, which is not necessarily new evidence, but probably a redundancy? Is that taken into consideration when calculating the association evidence score or strength among all the publications?
Yeah, that's a really good question. When we do scores within the platform, it's not a confidence score. It's a score it's kind of telling you the amount of evidence that's available. So in that case, actually, if a certain co-occurrence happens in a lot of different publications, it means that the score will be quite strong, because it's just telling you how much evidence there is available. So in that sense, so it is, does that make sense? It is redundancy, but it does strengthen the association, if that makes sense. Yes. I hope that answers the question.
Yeah, I think that's a very good question. I think this has been discussed within the team a few times, but we haven't found the right way out. So I think, as Elena said, the best way for us is to see redundancies as support, extra support for the evidence.
Thank you both. And for Santosh, could you please explain to everyone what license the annotated data in the corpus?
Yes, CC BY. It is mentioned in the repository as well. It's CC BY.
Wonderful, thank you. Are you rerunning the whole Europe PMC pipeline for every Open Targets release, or are these incremental updates?
So I believe. Oh, sorry, Santosh, go for it.
They are daily incremental updates, but we are constantly testing with the models and trying to improve the accuracy. Running deep learning models is very compute expensive, so we are coming up with new ways to solve this, and it's a daily incremental.
Thank you. Sorry, I feel like that's quite been covered. We try another one that's been less covered so far. So diseases tend to massively over-associate. How does the curation of efforts improve this? I think
So is it for me?
Whoever's
I don't know. The curation effects for gene disease association. So, for example, when we have given this task to curators, when we have assumed that there was an association already present, so some of the annotators marked it as there is no association, and also some of them marked it as a ambiguous based association. So I think we have to consider the context as well in when deciding the association type. So curation efforts will really help in finding those particular sentences where there is exact what we are referring to. And then we can use this to train the machine learning models with this right information. So curation will surely help us in this fight.
Wonderful.
Can I just if I understand the question correctly, I think one of the good things that we do when we curate this is also to use control vocabularies, right? Like the ontologies. So I think this also helps reading the context of where the matches are found, and And this is part of what Santosh was saying, like it depends. But we try to harmonize with the control vocabularies.
Lovely, thank you. So with 1 minute left, I'm just going to do one more question. If you have got any more, please do email the help desk for either Open Targets or Europe PMC, and we'll be able to get back to you. So how often do you update the text mining scores with the latest publications, or do you use the latest publications?
I think this is aimed at us. So every time we have a release, which is currently 5 times a year, roughly every 2 months, we will integrate the latest publications that we get from the Europe PMC data. So every time that happens, we will rerun it, we will update the scoring, and it should reflect whatever new publications are available.
Wonderful. Thank you very much to all of our speakers, Santosh, Helena and Annalisa. It's been great having you here, and thank you everyone for attending. Please do submit questions to the help desk if you do have any more. Thank you all again, and we'll see you next time. Bye.
Thank you.